But we're going to have a talk now on exploitation and state machines by Halvar.
Well, good evening. Does this work? Hello? Hello? Can you guys hear me? Okay, so good evening, and thanks for your patience in sticking around for this last talk. My name is Halvar, and I'll be talking about, as we mentioned, exploitation and state machines, primarily about, well, programming what I call the weird machines. So, what's this talk really about? In general, there's a lot of keywords that are being used in this community, like vulnerabilities, exploits, control, hijack, write for, and so forth. And a lot of this is very clear to everybody, but not written down. In the security community, we have a huge amount of folklore knowledge. Folklore knowledge meaning stuff that everybody knows, but that you can't actually find in the book properly documented anywhere. And then what happens oftentimes is that many, many years after folklore has been, well, developed and used and is known to everybody in the community, people outside of the community rediscover it and then claim it as their own invention. A nice example of it was the return-oriented programming ROP thing, where literally this was folklore knowledge in most of the security industry since 1998. And then in 2005 or so, 2006, somebody publishes a paper and claims to have invented it. And I think it's important to sometimes, while we're doing all the security research, stop and ask ourselves, what is it that we're doing? And write down a bit of this folklore knowledge. And this talk is a little bit about this. This is about asking yourself, what are we really doing when we talk about exploitation? And which parts of this can be automated and which parts can't be automated? So this talk will have two parts. The first talk is going to be about the question, what exactly are we doing when we write an exploit? And what is the right way to think about exploitation? Because exploitation is not a cookbook exercise where you just smash the stack and here you go. Nowadays, with mitigations, exploitation is quite complicated, and it's good to take a more abstract view on what we're doing. And then I will speak a little bit about something called the implicit state machine, which is kind of important. I reckon I'll just continue here. An important thing to know about this talk is that most of the ideas that I'll be discussing here are not actually my own ideas, but they're ambient background ideas, meaning everybody that has built a sophisticated exploit has more or less worked along the same lines, but might not always have formulated these ideas in a clear manner. If you look at the book The Art of Security or Security Software Assessment, TAOSA, there's a lot of very similar ideas discussed in this book, but they're not quite explicitly written out in this in a clear manner. Sergey Bratus termed the term weird machine, which I'm going to use quite a bit. So, important thing, this is mainly folklore knowledge. Now, when we speak about exploitation, before we speak about exploitation, we should ask ourselves, what's the right way to look at programs to begin with? And the traditional way to look at a program is just a set of instructions, and every instruction transforms the CPU state, or the computer state, into another state. That's a very traditional way of looking at it. I think that for the attacker, it's actually too fine-grained. Because, yes, as a programmer, I have the option of executing a single instruction at a time. As an attacker, before I hijack control, before I hack the system, I cannot ever execute a single instruction. I execute instructions in bulk. So the proper viewpoint for the attacker is not to look at a program as individual instructions so much, but as well, a machine where with every interaction with the program, I have an instruction, and that thing transforms the state of the application into another state. So the programmer, when he writes an application, defines a set of valid states that this application is supposed to be in, and the program is an implementation of this state machine that the programmer has in his head, and well, every interaction with the program transforms one state to the other. A nice example, like a concrete example to think about this, is an SMTP server, because you don't actually, as an attacker, care so much about the individual instructions in the SMTP server. You care very much about the different states the SMTP server state machine can be in. Am I authenticated? And so forth. So, right. Now, the proper way to look at programs is really to see them as finite state machines And every interaction with the program causes a transition from one state to another. And initially, at least if the programmer designed his application properly, all the states that are available to you are sane, meaning the states themselves do not violate security properties. The states do not just allow you to execute arbitrary code. And a really interesting thing happens when we start corrupting memory, because out of a sudden, our state space explodes, meaning we have all these different states, and we have a whole bunch of different transitions in and out of these states, and all of a sudden we get one state that should have never existed in the first place, and we get all the transitions out of this state into the next state that shouldn't have existed. So what's really happening is we corrupt memory, and we get into an absurd state, and then we continue interacting with the program, and the program transforms one absurd state into an even more absurd state, into an even more absurd state, and so forth. So we now have a new state machine. And this state machine has a gazillion states that the programmer never foresaw, that the programmer never intended to be there. And almost every instruction that you execute will end up in a crash. If you corrupted the heap, and you're not careful in the way that you continue interacting with the application will just crash. So we have a sort of computing device, and every time we interact with it, it executes one instruction, transforming one state into another state, and almost every transition will lead to a crash. Now this sounds weird, but it's not all that different from a regular CPU. Right? Because in a regular CPU, if I just randomly execute instructions, that thing will crash as well. So this weird state machine that, well, is created when we corrupt memory is what Sergei Baratos called a weird machine. So what is exploitation really? I think at its core, exploitation means setting up, instantiating, and then programming such a weird machine. Okay. Why is exploitation programming the weird machine? Well, the goal of an exploit is to reach a state of the application that violates security assumptions, ideally in the most egregious manner possible. And in order to get there, you have to somehow go from these bizarre states into another bizarre state that is useful for the attacker. Now, the traditional EIP hijack, where you overrode the return address, that was, in a way, just a form of, well, translating the weird machine into something that we understand. Because we don't know all the instructions and we don't know all the effects of the weird machine when we corrupt memory, but we do understand the individual x86 instructions. So if we hijack EIP, well, we now understand how we can program this. But in the end, we don't care really in which way we're performing computations inside of the process. We don't need to hijack EIP. We don't need to get control to do like weird stuff once we have memory corruptions. So what are the properties of weird machines? Well, first of all, they're application dependent, because, well, the application defines all the initial states, and the application defines all the transformations, and my interaction with the application defines what sort of transformations there will be. And therefore, every application will have a different weird machine, if you want. And weird machines are initial state dependent, meaning at the time of the attacker corrupting memory, there's a particular state that the attacker starts out with. And depending on this initial state, the different transformations will have really different effects. So a third property is that they're really hard to control. An attacker, like most of the time in writing a modern exploit, is spent in setting up the initial state in a way that the attacker can keep control of the weird machine as things get weirder. And even then, there's a lot of probabilistic risk. I mean, if you talk to anybody that does heap grooming or any sophisticated heap attack nowadays in a multi-thread scenario, you have inherent non-determinism. So as an attacker, you're trying to program a CPU for which you don't actually understand the instructions fully, and part of this is probabilistic, and you can't actually rely on things always behaving in the same way. So, what are examples, like real-world examples for people doing weird machine programming? Well, if you do, if you chain a bunch of code chunks together and then bootstrap into regular x86 code, this chaining of a bunch of chunks, like wrapping essentially, is a form of weird machine programming. But there's other things. Mark Dowd, a couple of years ago, had an interesting attack on, or an interesting way of exploiting a memory corruption, where he essentially patched out the restrictions in the Java interpreter or .NET interpreter or whatever. A full ROP payload is a weird machine program. But also, if you look at something like the Pwn2Own, not this year, but last year, the winner of that Pwn2Own created an information leak from a memory corruption, in essence by overlapping a regular string and a Unicode string. Or, well, he had a Unicode string, and then he overflowed with a regular string up until the last byte of the Unicode string, effectively unterminating the Unicode string, and then he read out the Unicode string again, and thus got a whole bunch of memory back. And that's a clear example of a weird machine program, because he's, well, operating with whatever weird states he's got in his memory to get stuff back. But there's much more. Any sophisticated heap exploit is essentially doing a convoluted weird machine program. So, what are the consequences of exploitation being weird machine programming? Well, the usual pattern in the industry is attackers find one particular method of making weird machine programming convenient. EIP hijack, ROP, whatever. And then a whole bunch of defenders who don't understand the meta-theorem that we're programming a weird machine. They only understand the one particular path that the attacker has chosen. And then they come up with a mitigation that makes that particular way of programming the machine difficult. And then the attacker's like, well, if I can't do it this way, I'll program it in another way. So you iterate this a couple of times, and in a way it's bizarre because it's almost like blacklisting of programs, but you're trying to blacklist a particular weird machine program. So one of the consequences is mitigations fail a lot. In reality, ASLR and DEP, if the attacker has sufficient time to prepare and the exploit is, or the bug is halfway decent, do not actually pose a huge obstacle. They cost time, but then they don't make things impossible. The other consequence is that forensics on an attack are extremely, extremely hard. Because if you see a crash for, like if a process crashes on your box, you really have no way of identifying whether an attack was in process or not, and what was happening. So, right. So, what does this mean concretely for the attacker? Now, first of all, ASLR and DEP doesn't matter nearly as much as people think. And another really important consequence, and that's something that is gaining popular support now, is when ASLR first became widely adopted, a lot of people said, well, if you want to exploit something now, you have to find an info leak. That is actually not true. You have to build an info leak. Info leaks are usually not found, but built out of existing memory corruptions. And, well, in some particular situations, you can even start programming the weird machine without having info leaks. Now, there's many, many, many ways that ASLR and DEP failed. I won't even get into all of them. So there's various FRAC articles, Mark Dowd did some work, Sodirov did some work, Tyler Durden, Nergal, just tons of them. So what I'll do in this following bit of the talk is I'll show one more example of bypassing ASLR and DEP, which is specific to the JavaScript bytecode interpreter SpiderMonkey, which is the default interpreter in Mozilla, but also the interpreter that Adobe Reader uses. So what can we do here? How can we start? First of all, SpiderMonkey itself takes JavaScript that is supplied by the attacker, and then compiles JavaScript into a bytecode. And this bytecode is put into memory, and they have an interpreter for this bytecode, which then interprets the bytecode as a stack machine in memory. Because the bytecode is emitted by compiling the user's JavaScript, the bytecode itself is trusted. It is assumed to be generated by the compiler, and is assumed to not be evil. And the bytecode is really powerful. It can do essentially whatever you want. A little bit convoluted, but it's powerful. You can add values, you can copy data, and so forth. So a few examples of instructions in the JavaScript bytecode. You've got a poppin, dupe, goto, swap, and so forth. So let's look at poppin. Poppin will, well, adjust the stack pointer of the simulated stack machine by a 16-bit value that you obtain from the bytecode. So you can start shifting the stack pointer around in memory arbitrarily. There's no range checking whether you're staying within range. Swap instructions, well, take stuff on the stack, swap them around. So now we can move a pointer through memory and swap values. Pop V, right, you can pop a value into FPR val. Set local ends up writing stuff again, and so forth. Now, the important takeaway for this is that if you can run arbitrary JavaScript bytecode, you can actually do whatever you want in that address space. It's difficult and it's complicated, but you can essentially do whatever you want. There's a lot of weirdness because JavaScript, or the SpiderMonkey interpreter, encodes type information in the least significant bits. So writing certain values can be tricky, but in general, it's quite doable. Now, so let's assume the worst possible bug from hell. And the worst possible bug from hell is you've got something that fell out of your fuzzer and you have no idea what is actually happening. And for some reason, you can't figure out what's happening either. And you can crash the application, but you can't crash it in a controlled manner, meaning every time you run it, it crashes differently. Or it crashes at the same spot, but it crashes with a different value. So what's happening is, let's say we have a write that we can control, but only slightly. Meaning the destination address, we can control it, but there will be a 24-bit random value essentially added to it every time we run the application. So it'll crash somewhere in memory, but we don't really know, or we can't really say where. We control the value that is being written, but we can't really control the location. So another thing is the write itself is double word aligned, so you only have about 22 bits of randomness. And you have to do, like you have to attack something that is ASLR'd and dept. Okay, how do you do this? Can we get reliable execution even though we have a really badly controlled write somewhere into memory and we can't figure out how to control things better? So the battle plan is, well, we make the JavaScript interpreter fill memory with a whole bunch of JavaScript functions. So we'll create JavaScript functions, and then we'll make the JavaScript interpreter compile them and put them into memory as bytecode. And then we'll make sure that every bytecode calls the next function. And then we call the first function of that bytecode, and the execution will go through all these functions in memory and execute one after the other. Now, we'll do this and interleave the bytecode with regular data. So you'll have JavaScript bytecode, data of the attacker, JavaScript bytecode, data of the attacker, and so forth. And then when you write into this, or when you randomly write your value, you write a JavaScript goto, like a JavaScript byte jump, into that bytecode, so that you hijack the interpreter and divert it into your data, and then you execute arbitrary bytecode, and then you can do whatever you want. And so yeah, we interleave JavaScript functions and data on the heap, and we make sure that the functions call each other. So if we call the first one, it jumps to the next one, and it jumps to the next one, and it jumps to the next one. Okay, so this is actually a diagram from a real-world implementation of this attack. What you see here is a tool that is very similar to Gera's heap draw, which essentially takes well, logs heap operations and generates nice diagrams so you can understand what's going on the heap. How do you read this diagram? Well, the x-axis here is time, and the y-axis is your address space. So whenever you allocate a block, this thing will start drawing a block into this diagram, and as long as the block is still allocated, the block stays green. And when the block is freed, the block, well, turns black. So what we see here is, we see how we're alternatively putting, well, wait, perhaps I should explain this better. So we see here how we are putting JavaScript bytecode data onto this heap. And why is it striped like this and not striped here? What we're doing is we're generating a whole bunch of JavaScript functions, and then we're freeing half of them, every second one. So out of a sudden, when the garbage collection of JavaScript kicks in, you see this line here, where every second block turns black, which means we now have gaps between the JavaScript functions on the heap. So JavaScript function, gap, JavaScript function, gap. and then we allocate attacker data into it and fill it up again. So this is what's happening on the heap here. Yeah, this is an explanation of what I just said. You can see very nicely here if you zoom in how the garbage collection kicks in and then starts freeing all the functions that you let go. Okay, now what JavaScript functions do we want to spam into memory? Now, we want to spam JavaScript functions into memory that we can easily turn into a goto. And the important thing for this is that whatever code we're spamming needs to create double-word aligned repetitive patterns of JavaScript bytecode. And the easiest way to do this is to have many V++ JavaScript instructions, which means, okay, increment an argument. Because that gets compiled to the following JavaScript bytecode, 6300, which means increment argument at index 0, pop from the stack. So by having many of these V++, you spray repeatedly 63000051, 630051, and so forth. And then, after a while, you call the next instruction in the chain. OK, so by spraying this, we now get all these JavaScript functions, and we interleave them with data. And then we overwrite the JavaScript, or we randomly write into memory, but we end up overwriting it with a JSOP goto, which is 06xxxxxx. Or alternatively, you can use a 32-bit displacement with 8b and then whatever value you want. And you get control. So what do we learn from this? First of all, of course, this is very brief in a presentation now, but it takes a lot of time to actually pull this off. When you end up doing this, like I didn't do this in an afternoon. It took a lot of headache and a lot of reading SpiderMonkey source code and so forth. The other interesting thing is that if you have a JavaScript interpreter in your address space, you can turn the most annoying, weird crash into code execution, well, in a fairly reliable manner, even if the crash is really a nightmare crash from hell. I mean, we had a 25 megabyte margin of error in targeting where we're writing, and it still works quite nice. This should work in IE and Firefox as well. It doesn't work very well in Chrome, because Chrome does direct-to-JIT, which means Chrome doesn't have the intermediate bytecode, really. It directly JITs every JavaScript that comes in, which makes things a bit more tricky. Any questions so far? All right. So a few things. We do not necessarily need an interpreter. It's very easy to take away from this talk that yeah, there needs to be an interpreter. But the important thing is that, first of all, there's many interpreters everywhere, right? You've got PostScript interpreters, glyph scaling. I mean, in Windows kernel land, you've got interpreters for true-type font scaling and all sorts of madness. There's Flash, Python, PHP. If you look into your arbitrary browser nowadays, within that browser, you've got the JavaScript interpreter, you oftentimes have a PostScript interpreter, and you've got a Flash interpreter, and so forth. So they're everywhere. But you don't need the interpreter necessarily. The big takeaway, or the important thing, is that whenever you can repeatedly interact with the application, you have a full programming environment, and you just need to figure out how to program this. The interpreter hijack is actually just one of many instantiations. And also, as an attacker, it's not always a good idea to be obsessive about getting EIP. There's many things you can do without getting EIP that will be much more useful, and stability is your friend. So, right. There's lots of people that have done work on this. Sergey Bratos discussed some of this in 2009. The Taosa crew has done a lot of, or has formulated a lot of similar stuff in their book. Stefan Esser did very similar stuff on the PHP interpreter in 2010. Mark Dowd did some stuff in 2010 about this. There's probably more, I must have forgotten many. Right, second part of the talk. The implicit state machines. And this is mostly about things where we, like as species at the moment, fail. Like things that we're really not very good at. So the weird thing is that everybody that writes an exploit knows about the implicit state machine in a program, or about the implicit state machines in a program, but very few people actually mention this when they try to do something. So you see a lot of academic papers on automated exploitation. And they usually want to build the dream pipeline of every vulnerability researcher, where you throw a program in at the beginning, and it starts doing static analysis to find bugs, and then tries to automatically do input crafting to reach the vulnerability, and then it tries to automatically do an execution hijack. That's what everybody's pipe dream is. And then they argue about, okay, we can build this, we can do dynamic symbolic execution, we can ask an SMT solver to build input for a particular path. But a very, very common mistake that is made by everybody, and that is not mentioned in the papers that they publish thereafter, is the viability of a particular program path is very dependent on the application state. So if you ever write, like if you do patch reversing and you try to write an exploit from a patch, you get a bug in a program somewhere, so you know there's the vulnerability, and then you try to get a path. And then you try to build input for that path. And then halfway through the path you realize, oh crap, in order for this path to be legitimate, this global variable here has to be 23. But it's not 23 now, so I have to somehow get the program into state 23 first. So you go to the next path, which, oh yes, the global variable is being set to 23 over here. You start building input for that, but in order to execute this path, you have to have the global variable first in state 24, and so forth. So people completely neglect that without understanding that state machine behind there, this stuff just won't work. And unfortunately, the incentive structure in today's world is such that you don't get any credit for publishing when exactly things don't work. Could somebody please provide his password for this thing? Thank you. So the thing is that this implicit state machine is something that will bite you every single time that you try to execute a particular path. And it's really important to keep this in mind. And the trouble really is that, or the reason I think why people don't write about it is that we don't have good methods of dealing with these state machines. We've got no algorithms on how to extract that state machine from an executable. We've got no proper way of making the problem tractable. So, right. Now this slide is essentially a repetition of what I just said. So many people go down the route, let's take a program path, let's generate constraints, let's feed them to a constraint solver, wait for a result to come up, and let's then, I don't know, say we've built input for a path. The trouble really is that global state of the application almost always messes with you. Think about SMTP, and SMTP is a super simple protocol. Now think about any more complicated protocol, and you've got so many global state variables that your path will depend upon that it's really hard to get stuff done. So summary of all of this is ignoring the implicit state machine is a very bad idea, because if you want to get anything done, you can't ignore it. And well, we don't have any methods to deal with it yet, but it won't go away by ignoring it. So perhaps we'll come up with methods in the future. Another thing that comes from all the state machine stuff is determining non-exploitability and the hardness of this. Now, a lot of people run into the problem that they start fuzzing, and then they start scaling up fuzzing on a distributed system with a couple hundred computers, and then they end up with all these crashes, and they ask, hey, how can I tell whether this, which crashes are useful and which ones aren't? And the trouble is that the crash itself is a symptom. There's always a root cause somewhere in the program, but it can be extremely difficult to find, and it's semantic in nature usually, meaning somewhere the programmer misunderstands something or misconstructs something, and the fact that the root cause is oftentimes semantic means it's very hard to automatically find it, because semantic means it's a problem in meaning. And computers are not very good in dealing with something as vague as meaning. So the other thing is that a crash can be arbitrarily far removed from the actual cause of the bug. I mean, a server can crash 2 hours after memory got corrupted, and there need not be any trace of how the corruption led to the crash anymore. So I find it really amusing when people use things like bang exploitable for this, because bang exploitable is essentially a biased, like a coin flip. You can't actually determine from a bang exploitable output whether something is not exploitable. I mean, if bang exploitable says it's exploitable, it probably is exploitable. But if bang exploit says it's not exploitable, it might still be exploitable. There's just very little information in that claim. One thing that I did after I did the JavaScript bytecode hijack is I asked friends of mine that had done fuzzing to send me all the crashes that they think are non-exploitable, and I looked at a few of them. It was hilarious because there's actually a lot of them that will just exploit just fine. And I was too slow in the next slide again, sorry. I'm not doing this to piss you off. I can just hurry up with the next slides, don't worry.
Okay. Just touch the...
Yeah, I'll start monkeying around on the screen. Okay, another important question is, we've seen static analysis for a long while now, and I mean, there's almost 10, 15 years history in static analysis on source code. Why exactly has static analysis not killed all our bugs? Why do we still find like ridiculous overflows in OpenSSL last week? Right? So if you ask somebody that does a lot of static analysis, your answers are usually going to be something like interprocedural analysis is really hard, C++ analysis is really hard, or my tool will find all the bugs next year, or the tools aren't deployed widely enough. While most of these things might be true, there's other reasons. So what I did with a few friends at one point was we looked at existing historical bugs in critical applications. And we tried to reduce them down to the smallest possible example that still exhibits the same bug. And then we tried to understand whether a static analysis tool would be able to find this issue or would not be able to find this issue. And it turns out there's many really simple vulnerabilities that are impossible to find with any tool, but not only with any tool, but even with all published theory. So you can go through academic papers, and you won't find any paper that would provide a theoretical framework that would properly identify that overflow. So now, the important thing is when I say properly identify an overflow, I'm not speaking about the default excuse of people that do sound static analysis, which is safe approximation, which essentially means I'll say it's vulnerable if I can't make any other statement. Because the measure of quality for a static analysis tool needs to be you give it the same code pre and post patch. And if it can't distinguish this one is safe and this one isn't, then it's not terribly useful, right? I mean, the value of a static analysis needs to be evaluated versus, well, distinguishing power between vulnerable and non-vulnerable. My favorite small example that I like to keep in my head to think about all the time is the crack address overflow from SendMail a couple of years ago. And you can reduce it to a very small example. You can reduce it to 60 lines of C code, one single function, standard stack overflow, no heap allocation whatsoever, nothing complicated, but even this very simple example cannot be identified with any modern static analyzer in a proper way, or cannot be distinguished from the non-vulnerable version. So I've got some code here on screen to show this. And this is the vulnerable code. And what's happening here is we have some local buffer that's allocated, and we've got this small loop. And this loop essentially looks like copies stuff into a local buffer, and whenever you see an opening bracket, it switches this internal state machine to, oh, now we're inside of a quotation, and it makes sure that the upper pointer that limits the buffer to the top gets decremented by 1, so there's enough space for the closing bracket. Okay, so open a bracket, decrement the pointer, close the bracket, increment the pointer again. And then open a round bracket, and we see this out-commented line here. And this is what actually makes the code vulnerable. Because when they open the bracket, they forget to decrement, but when they close the bracket, they increment. So what the attacker can do is open bracket, close bracket, open bracket, close bracket, and the pointer will slowly be lifted or moved outside of the buffer, and too much data will be written. Now, the trouble is that, well, not the trouble, but if you plot this as a state machine, it's actually a very, very simple state machine. There's 4 states to this only, which means quotation true, round quote true. Well, you've got 2 Boolean variables. You've got quotation and round quote, and they can either be true or false. So you've got 4 states of the state machine within that loop. And you've got these transitions. The trouble is that in order to reach the vulnerability, you need to cycle through this cycle here repeatedly, 30 or 40 times, and only then your pointer is out of bounds and the thing is vulnerable. And then we have a standard stack smash. Now the trouble is that when you do regular static analysis, what will happen is that multiple different states will be merged into one. So what happens is, inside that loop, the static analyzer will say, okay, these variables can have the value 0, 0, and now I have to merge that with this other state 0, 1. And the static analyzer will then say, okay, this one variable here can have state 0 only, and the other value can be 0 or 1. And because you now introduce these weird summary states that summarize multiple states in the actual state machine, you get transitions that are not there, and then you get false positives. So, right. Most of the static analysis things will try to map program lines to descriptions of the possible states of the application. And they have to combine multiple states into one. And when they combine multiple states, you get an explosion in the states that they can reason about, and they get a false positive. There's other tools like Clay that will just do dynamic symbolic execution and try to execute all possible paths through this loop. But the trouble is, we need 30 or 40 iterations through that loop to get somewhere, and they need to take the right branch every time. So the complexity of finding the right path is 4 billion paths, and you never reach it. So, right. Okay. The summary that you can take away from this is that even if we could solve the problem of interprocedural analysis, even if we could do C++ code, even if we could scale this up to all the source code, we really don't know how to deal with a simple memory copying loop like this. And that's actually a very, very, I found it really interesting that you can create a small example that you can write. Like, the nice thing is it's small enough to keep in your head. It's small enough to sketch out on a piece of paper in a bar. Yet still it breaks essentially everything. And that makes for a nice example. Right. Okay. Now, what's the summary to take away from this? First of all, when you try to do automated input crafting, and I know many people try this because it's the one thing that everybody wants, be sure that you don't ignore the fact that there is a state machine. There's a state machine behind that application somewhere, and you need to not ignore it. If you ignore it, you'll spend all this time building a dynamic symbolic executor and a SAT solver and all these things, and then you'll figure out, shit, without that state machine or without understanding the state machine, I can't actually do this. Second thing to take away, determining whether a particular crash is exploitable is kind of hard. You have to have a very thorough understanding of what's going on. And it's not quite clear to me how anybody would do this in a large-scale automated manner. Another thing to take away is static analysis is very, very powerful for many things. Interestingly, standard integer overflows are surprisingly easily caught by a lot of static analysis algorithms. At the same time, at least from my perspective as a security researcher, it's really interesting to think about what are the bugs that can't be dealt with static analysis. Right? Because those are the bugs that you'll be finding once everybody has sophisticated tools rolled out. And so the takeaway here is that small loops with a state machine will easily break most sophisticated static analysis algorithms. Another important thing is that for all the things that I'm criticizing here, it's very, very easy to construct examples where they will work. Right? And the usual way to publication in this world is you come up with a theoretical construct, and then you find, or you construct one example where it works, and then you submit a paper. Unfortunately, if you actually want to get stuff working in the real world, you can't ignore, like, you don't get to construct reality for your convenience. That's right. Any questions? I think I'm at the end of my slides. Yes?
What do you know that you check all the states?
Sorry.
When you're crafting, when do you know that you have tested all implicit state machine states? When do you know how to stop? When you've just examined every situation that you come across?
Right. So is the question, how do you examine the state machine?
No. When do you know that you've done checking the implicit state machine for each
right. Okay.
draft you make?
Yeah, that's a good question. I don't know whether there's a way of knowing, right? I think a very, very important I think something that's important to keep in mind is that humans are sometimes much better at understanding these state machines than automated methods. When you look at the crack address state machine, if a human looks at it, he will see, oh wait, the intention of incrementing this pointer is making room for a closing bracket. Now, if this is the intention, is the author of the program actually doing it everywhere? And so there's a very, very non-mathematical aspect to it. It's like, you as the person reading the code, you think about what is the guy writing that code trying to do? And then you have an intuition for weird states. If you think about chess playing programs do this extreme forward brute force analysis, and they have a scoring function for beneficial states, essentially. And what we don't have in security analysis is a scoring function that can automatically tell you whether this state is weirder than the other state. Because as a human, you read this code for 2 lines, like 2 iterations, and you're like, something is wrong here. Like you just do 2 or 3 iterations in your head, and you're like, wait, why can I move this pointer? But a machine can't quite do this. So yeah, I'm not sure whether I actually answered your question, but it's...
Well, yeah, because sometimes it's overwhelming when you just find a solution and you just think you just did it, and you don't examine any other possibilities or other paths that the state of the program might be there. Yeah. So,
at least for small state machines, I just sit down with a pen and paper and I draw them out on paper, and then you have 2 people that actually sit down and verify it. It's
exactly.
It's a very low-tech solution, but
sure.
Right. Any other questions?
Right. No.
Then thank you for your time and enjoy the evening.